power plants are the biggest source of electricity worldwide. They convert the energy available in the coal to electricity. In India, approximately 80% of generation comes from coal-based power plants. Coal from coal mines is brought to power plants by various modes like by rail, road, ropeway, conveyor belts, and merry-go-round systems. A huge amount of coal is usually supplied through railways. A railway siding line is taken into the power station and the coal is delivered in the storage yard. The coal is unloaded by means of a wagon tippler or a track hopper system. This video shows coal unloading in track hopper. Track hoppers are mainly used for coal storage and handling in power plants. In this system, coal unloading is done from BOBR wagon. That means bogie open, bottom rapid discharge railway wagons. Each BOBR wagon can carry approximately 45 metric tons of coal. Hence, each unit of track hopper carrying 15 BOBR wagons can unload 675 metric tons of coal in 30 minutes approximately. Daily requirement of coal in 500 megawatts power plant is about 6,000 metric tons of coal, having GCV as 4,500 kilocalories per kilogram and considering heat rate of 2,300 kilocalories per kilowatt hour. Now we come to the track hopper. It is made from a large number of mechanical items like steel grating covering the RCC hopper along with the railway track, RCC hopper of 210 meter length and 8 meter width, feeder at the discharge side of the hopper, and conveyor belt located at the discharge of feeder. Hopper is a V-shaped RCC container to hold and discharge coal through its bottom chute. Below it, feeder is located which feeds coal to the conveyor belt. Feeder plays an important role in evacuating coal from the hopper. For instance, if there is no feeder, coal discharge to conveyor belt may be erratic. If it gets coal which is lesser than its capacity, then it will run at partial load. In the other case, it may receive excessive coal which will overload the belt and may cause spillage and even failure. The feeder, therefore, feeds the correct amount of coal for its optimum performance. The conveyor belt is used for transporting coal horizontally or inclined upwards. The conveyor belt is mainly comprised of a reinforced rubber belt, troughing idlers, or rollers. Troughing idler consists of a center idler and two wing idlers. These wing idlers are cranked up to an angle called the troughing angle. Here, we can see the transportation of coal from the storage yard to crusher house through conveyor belt. Manual stone picking is done at various suitable locations of the conveyor belt. At the discharge end of conveyors, ILMS, that is inline magnetic separators, are provided. They are used for continuous and automatic removal of unwanted tramp iron pieces from coal. As power supply to ILMS is on, electromagnet is energized and its belt starts rotating. If tramp iron along with coal comes in magnetic field area, it is attracted towards electromagnet. Its self-cleaning belt carries iron pieces beyond magnetic field and it drops off iron pieces into a separate hopper. After iron pieces are segregated, coal is discharged to roller screen. Roller screens are suitable for separating fine coal from coarse coal. Main components of roller screen are drive unit, transfer shafts with eccentric disc rolls, and longitudinal shaft. Transverse shafts receive motion through longitudinal shafts operated by drive unit. Due to rotation and special shape of eccentric disc, coal is lifted and pushed forward to the crusher. Smaller sized coal passes through the opening between two consecutive eccentric discs and is thus separated and collected. Only coarse coal is sent to crusher, and therefore this preliminary screening is very important for reducing unnecessary load to crusher. We can see that the coarse coal flows down the chute of roller screen and is fed to the mouth of the crusher. This type of crusher is called ring granulator crusher. Such machines are fabricated from heavy steel plates and are specially designed for continuous crushing of coal. It mainly consists of rotor shaft, ring hammer, crushing plate, sieve plate, and discharge opening. Crushing of coal takes place by two types of action. One is by the impact of ring hammers and other is by rolling compression between crushing plate and ring hammer. Crushing reduces size of coal up to 20 millimeters. These machines are ideal for crushing coal to a suitable size for pulverization. Now this crushed coal is fed to coal bunkers for pulverization in coal mills and then for burning in furnace. In case coal bunkers are full, this coal is sent for stacking or storage in coal storage yard through conveyors and transfer points. When level of coal in bunkers reduces to a certain level, stacked coal is reclaimed and sent to coal bunkers. Now you will see how coal stacking or reclaiming in coal yard is done with the help of bucket wheel type stacker reclaimer. This huge machine is called bucket wheel type stacker reclaimer. It is a huge rail mounted machine which can stack coal on either sides of the track rail. Stacker reclaimer is composed of long travel mechanism which includes track rail and moving bogie wheel assemblies. Some other parts are bucket wheel and drive arrangement for reclaiming coal, boom conveyor which is reversible conveyor belt, slew bearing of large diameter fitted at center of the machine, It has three basic movements. First is traveling, that is the movement of stacker or reclaimer on rail track. Second is luffing, that is the raising and lowering of boom conveyor. And third is slewing, which is revolving of boom conveyor with the help of slew bearing. During stacking mode, crushed coal is fed from yard conveyor to boom conveyor. Boom conveyor then carries and discharges coal from its end and makes various stockpiles. In this mode, coal will flow in forward direction as shown. On the other hand, reclaiming is done by combining rotary motion of the bucket wheel with slewing motion. Rotary motion of bucket wheel reclaims coal from stockpile and slewing helps in reclaiming further. Bucket wheel discharges coal to boom conveyor. Now, boom conveyor moves in reverse direction for feeding coal to bunkers as shown. Coal bunkers feed coal to coal mills, also known as pulverizers. The mill shown here is XRP803 type bowl mill. This is medium speed vertical mill with 3 numbers of conical grinding rolls, bowl shaped grinding platform, and a gearbox mechanism. Its nomenclature can be understood as 80 stands for bowl diameter in inches, 3 is the number of rollers, X is the frequency of power supply, that is 50 cycles. R stands for Raymond, the name of inventor. P stands for pressurized type with PA fan before mill. Otherwise, it may be S, means suction type. Gearbox and drive rotates bowl of the mill. Crushed coal enters through coal feed pipe and falls on rotating bowl. The rotation imparts centripetal force on coal particles and forces to outer periphery to press coal between grinding rolls and bowl. This huge structure is known as a boiler. It burns down powdered coal as primary fuel and produces high-pressure steam. Here we can see that the boiler is made up of various tubular structures of different types. In this video, we will explain the role and function of these tubes. Boiler is mainly divided into 3 zones depending upon the type of heat transfer taking place. First is the radiation zone, where heat is transferred through thermal emission. So this zone is around a furnace where coal is burnt. Second is the convection zone, where heat is transferred by the movement of hot flue gases. So this area comes under the convection zone. Third zone is a combination of two, that is radiation plus convection, and therefore comes between the two. It comprises a furnace, boiler drum, and many tubular structures, say water walls, superheaters, reheaters, and many headers. Let's have a look at its main components. First is the furnace. It is equipped with coal burners at all 4 corners, repeating at 3 or 4 levels. This arrangement is known as tangential firing. Powdered coal from the mill is discharged from the nozzle of the burners and is ignited. It produces an intense fireball which spreads out and fills the entire furnace area. Now we come to downcomers and risers or water wall tubes. Downcomers are tubes that supply water from the boiler drum to distribution headers at the lowest part of the furnace walls. Water walls or risers are a series of tubes welded together to form walls of the combustion chamber. It has typically 2 side walls, rear wall, front wall, floor, and the roof section. Water from distribution headers enters into all the water walls. It gets heated up in the furnace area and partially converts into steam. This water and steam mix runs through the risers up to the boiler drum. Boiler drum is a high-pressure vessel which separates steam from water with the help of drum internals. After separation, steam is sent to superheaters for further heating and water is sent to the distribution header through downcomers, and the cycle is thus repeated. We can see various mountings on boiler drum like main stop valve to stop or allow flow of steam from boiler to the turbine. Safety valve blows off excess steam and maintains pressure inside the boiler drum. Feed check valve, which is NRV type and controls supply of feed water. Pressure gauge to indicate pressure of steam. Drum water level gauge to show water level in the drum. Blow down valve to control dissolved solids in boiler water. Also, there is a manhole on the boiler drum body which allows entry for maintenance and cleaning during shutdown. After the boiler drum, saturated steam goes to superheaters for further heating. It goes first to low temperature superheaters located in the second pass. From there, it goes to the platen superheater and then to the final superheater situated in the first pass of boiler. After that, superheated steam is sent to the hpturbine. Thus, we see that superheaters increase enthalpy of steam, which increases work in turbines. It utilizes heat from flue gases and increases efficiency of the boiler. After expansion and HP turbine, steam temperature and pressure decreases, and so it is sent to the reheaters. In the first stage, it goes to the primary reheater, and then it goes to the final reheater. Reheating utilizes heat of flue gases and increases steam temperature and pressure. Reheated steam is sent down to the IP turbine and then it is fed to LP turbine. Now we come to the turbine hall, which looks like this. Smallest in size is the HP turbine, that is the high pressure turbine, then IP turbine, which is intermediate turbine, and third is LP turbine, which means low pressure turbine. In its cross-sectional view, we can see different parts of the turbine like turbine blades, rotor, and shafts. There are two types of blades in a turbine, moving blades and fixed blades or nozzles. Together, they are called stage. They have an airfoil shape. Moving blades are attached to the rotor, which rotates, and fixed blades are attached to the casing, which is static. The steam flows through one set of moving blades, which rotates the shaft, then it is directed to the fixed blades. Fixed blades increase the velocity of steam and guide the fluid to hit the next moving blade at an optimum angle. When the turbine shaft starts rotating, it also rotates the shaft of the generator, which is coupled along with. This is how turbines work. As discussed earlier, the superheated steam goes to the HP turbine. Here it expands, loses its temperature and pressure. HP turbine exhaust steam is then sent to reheater and reheated steam is sent to IP turbine inlet. After expansion in LP turbines, the steam pressure as well as temperature goes very low. Finally, this low energy steam is sent to the condenser for condensation. This condensate water is used as feed water. The Rankine cycle graph shown here can be very helpful in understanding the benefits of superheating and reheating. In the graph, the area shown in red color depicts extra energy and work due to superheat. Similarly, the area shown in yellow color shows the same due to reheat. Next to LP turbine, we can see generator mounted on the same shaft. Therefore, when turbine shaft rotates, it rotates generator shaft also. Generator is equipped with two main parts, namely stator and rotor. The stator consists of a group of insulated coils arranged in a hollow cylinder. The rotor is a rotary electromagnet located inside the stator and mounted on AC motor shaft. When it spins, it induces AC current and generates electricity. The complete process of energy transformation can be understood as shown. Chemical energy of coal is converted into thermal energy of steam, which gets converted into mechanical energy, which causes rotation of turbine blades along with generator rotor. This movement finally transforms into electricity. Transmission is the bulk movement of electrical energy from a power station to an electrical substation close to the electricity consumers. The interconnected lines form a transmission network or power grid. When electricity is generated at a power station, it will typically be anywhere between 11 kilovolts and 33 kilovolts. It is then stepped up using generator transformer to a voltage between 132 kilovolts to 765 kilovolts or more, depending on the distance of transmission. The longer the distance, the higher the voltage level. Generally, power is transmitted as high voltage, three-phase alternating current. However, high voltage direct current, say HVDC technology, is used for greater efficiency over very long distance transmission. From generator transformer, stepped up power goes to the switchyard, which is equipped with current transformers, voltage transformers, isolators, circuit breakers, bus bars, and more. Main role of the switchyard is transmitting generated power to different load centers, connecting and disconnecting of the transmission lines as per the requirement, protecting transmission system by isolating faulty network, maintaining system frequency within limits. Electricity is transmitted through transmission network to different substations located near the load centers. Substations consist of high voltage electrical equipment like transformers, switchgear, circuit breakers, and associated devices. Transformers step down the high voltage electricity to a much lower voltage suitable to send out on distribution wires. Consumers are broadly classified as domestic or residential. These consumers are supplied through the distribution network, which is generally 11 kilovolts, and using distribution transformers, 400 volt supply is provided to end consumers. However, some of the residential societies take connection at 11 or 33 kilovolt levels. Commercial or industrial consumers. First is the low tension consumer. Generally, these are very small units and are supplied through 11 kilovolts to 400 volts distribution transformers. Second is the high tension consumer. These consumers might take supply at any voltage between 11 kilovolts to 400 kilovolts. Generally, small and medium industries take supply at 11 or 33 kilovoltage level.
That's all for today's video. Stay tuned for more such informative videos.